The floor is yours, Sally.
Okay, thank you very much for the invitation to give this colloquium. I love talking about Higgs physics and precision physics and what we might find in the future. So today I'm going to give an overview of my thoughts on looking for new physics through precision measurements. And of course, we all know that we haven't found any new particles at the LHC. And I said yet because what we would really hope is that someday in the future, we'll find a clear signal that there's some new physics there. But in the meantime, the limits are really getting higher and higher. I've got an Atlas search here on the left and a CMS search here on the right. And I think intentionally you can't read what they're looking for, but most of the limits are over a TeV. So these red arrows are a TeV. Here's red arrows here. And you can see that in some cases, the limits stretch up 5 to 10 TeV, but in almost all cases, they're at a TeV. So that means it makes sense to think of what happens if there's no new light physics. That's not to say that there can't be light physics. It's just that everything we've looked for is heavy. And also, this is now coupled with the LHC measurements in that they really look, quote, standard model-like. There's an impressive agreement between theory and experiment over many orders of magnitude and in many different kinds of processes. So on the left here, we see many different searches for W's, searches for Z's. Down here, we're looking for Z pairs. Down here, we're looking for 4 top quarks. So in all these processes, and they have cross sections going, here's 10 to the minus 5 up here, 10 to the 6 picobarns. Everything lines up, unfortunately, very closely to theory. So here's data over theory, and you can see that as you get to some of the smaller cross sections, the uncertainties are bigger, but there's really no indication whatsoever that there's any interaction beyond the standard model-like. So what does this mean for theorists? Well, we start with the Higgs boson because that's the most radical thing we found in the last decade. And even for the Higgs boson, you see that it really fits the standard model. So these are the couplings to the standard model on the y-axis here versus the particle mass. And again, it lines up just bing, bang, boom, right on top of the standard model prediction, even when you have a linear plot. So up here are log plots, down here are linear plots, and you can see the muon, the tau, the b. There's no indication of anything that's not standard model-like. And the important thing to note about the standard model is that it doesn't have free parameters in the plots. The particle masses are inputs, but after you input the particle masses, everything is predicted. And it's this definiteness, the fact that there are no free parameters that allow plots like this to calculate on an absolute scale data over theory or the Higgs couplings without any free parameters. So that says that looking for new physics is going to be really hard. So where should we look for new physics? So it could be many orders of magnitude. Here's 10 to the minus 29. Here's the Guts scale. And here are the known elementary particles right in the middle. So the Higgs is here, about 100. Neutrinos are down here. And so different questions suggest searching at different scales. So if I'm looking for dark matter, I might look at the lower side of this plot. If I'm looking for neutrino masses, I might construct some seesaw mechanism up at the upper end. But I'm going to think about the kinds of models which might solve the hierarchy problem, which might tell me why the W and the Higgs are sort of 100 GeV as opposed to at the Planck scale. So current data doesn't give us any hints about where to look on this plot that goes from 10 to the minus 29 to 10 to the 19th, but I'm going to focus on this scenario kind of in the middle, where the new physics is heavy, but it's on the order of TeV, 5 TeV, 10 TeV. So the new physics is assumed to be heavier than the weak scale, but not up at the Planck scale. So there's no shortage of models that predict more Higgs particles, and there's no shortage of models that predict all these searches I showed you a few slides back, but there's no evidence. So how are we going to look for new physics? Well, I could hope that there's some resonance, some bump here, and that's the easy way. And if you remember, for example, the 750 GeV of a few years ago, it was 2 photons making a bump. So we could hope that this is going to happen. But what I'm going to talk about today is looking in tails of distributions. So out here at the tails, where the cross section is small, the errors are larger on the experimental data, and the uncertainties are larger on the theoretical calculations. So how am I going to go about looking for small deviations in tails of distributions? Well, first of all, it's hard. So I'm going to assume that there's this hierarchy of scales. I'm going to assume that there's some new scale, which I call lambda. Okay, so lambda is some high scale. This is a scale where I have a beautiful, perfect theory that explains why dark matter exists, why neutrino masses exist. This is some complete model up here. I don't know what it is, but it's the only thing I'm going to assume is that it's much, much heavier than the W mass. So there's some complete theory up here at the scale lambda. So any new particles that might happen to exist, any new symmetries are going to be at this very high scale lambda. So I'm going to talk about physics at the W mass. So at the W mass, or the weak scale, we have only standard model particles in the theory. Experiment supports this idea that at low energies, all we have is a standard model. And we're going to expect the effects of the heavy particles, whatever happens at this very high scale lambda, to be suppressed at the scale where we measure the physics today at the LHC. And this is a really sad way to look at physics. This is a sad scenario where there's no intermediate scale physics, where there's no physics popping out at 200 GeV. So it starts from the idea of high scale decoupling, because I said here that we expect the effects of the heavy particles at low scales to be suppressed. So this means I've assumed something, and this means I've assumed decoupling. So let me just go through decoupling in its very, very generic form. So suppose there's some new particle X, some Z prime that weighs 10 TeV, say, some heavy particle. So this new particle, we assume it has a mass, mx, much, much bigger than the W mass. So if I look at some scattering process, say E plus E minus goes to E plus E minus, there's a nice process with this Z boson, the standard model Z boson. So in the standard model, this is just the standard model coupling, say G squared over MZ squared. Now my particle X will also contribute to the same scattering amplitude with some Gx over Mx here. So the scattering rate is a standard model rate from G squared over Mz squared, plus the interference of my new particle with my standard model Z, and this will be suppressed by 1 over the heavy mass squared to give me the standard model. So in this scenario, if M sub X goes to very large, my new physics is very heavy, everything looks approximately like the standard model. So this assumes that this G sub X is weak, that it's not something which would spoil this coupling. So as I construct a standard model effective field theory, what I'm implicitly assuming is that all the heavy stuff decouples, that I don't see any effects which are very sensitive to 1 over mx. So we assume that the heavy stuff just decouples, its effects are suppressed by 1 over the heavy mass squared. But of course, you all know that the Higgs boson doesn't decouple. The Higgs boson couples to standard model particles proportional to the Higgs boson mass. So if I had a mass upstairs here, it would spoil this argument. So this argument really actually makes some strong assumptions. So this is a way to indirectly discover new physics by looking at small effects. I'm looking at these effects, which are essentially 1 over m heavy mass scale. So the first example of doing this started with the Fermi theory, where way back when we measured muon decays to an electron plus 2 neutrinos, and we knew there were 2 neutrinos by looking at angular and energy distributions. So if I have this process, the muon decaying to an electron and 2 neutrinos, this is a 4 fermion interaction, which scales like the Fermi coupling constant times the energy squared. So an interaction that scales with energy squared is eventually going to violate unitarity, so it will violate conservation of energy. It grows with energy squared, and so it cannot be. But then we all know in the Standard Model that the W boson comes in to save the day. So the W boson is exchanged between the muon and the electron, the muon neutrino, electron neutrino here. So the W boson means that the cross-section doesn't grow with energy, but it's cut off by the W mass squared. So this was an indirect way to discover new physics. We measured muon decay, G Fermi, but we inferred that there must be something like the W mass to make it not grow with energy. So the goal is to apply this lesson to TeV scale physics. And it starts by constructing an effective field theory. So here's our first effective field theory. My full theory, my theory at the very high energies, is a Standard Model. It's a renormalizable, consistent dimension 4 theory. So at high energies, I've got the Standard Model, and the interaction of the muon with the neutrino and the electron is just given by this interaction, psi bar gamma mu psi, and there's a propagator here for the W, which is Q squared minus MW squared, and it's got the Standard Model coupling G squared. Whereas at low energies, I've got my effective Fermi coupling, G Fermi here, and the same interactions. So the effective field theory is constructed by saying that at the W mass, they must give me the same thing. So I must get the same thing from my high energy theory, the Standard Model, and my low energy theory, the effective theory. So I will match. So that tells me G Fermi is just given in the parameters of my full theory. So G Fermi is predicted in terms of the weak coupling constant G and MW squared. And this is generalized in effective field theories so that we can predict the coefficients of low energy effective interactions in terms of the high scale physics. So I'm going to construct an effective field theory framework, and it's really a very, very simple framework. And essentially, all you need to know is on this slide, because the effective field theory assumes that we have the same gauge theory as we have in the Standard Model. So the gauge theory of the interactions is SU3 for color, SU2 cross U1 for electroweak, and there are no new light particles. We haven't seen any, we'll assume there are no new light particles. So the really big assumption of this framework is to assume that the Higgs particle is part of an SU2 doublet. So the Higgs boson is assumed to be in the same SU2 doublet as it is in the Standard Model. And this assumption defines what we call the SMEF, the Standard Model effective field theory. So it's a low energy limit of an effective field theory with towers of higher dimension operators. So the Standard Model here is a low energy limit. So we construct our interactions as an expansion around the Standard Model. So it's exactly like my decoupling example where I had the Standard Model and then everything else was suppressed by 1 over big M squared. So here, everything is suppressed by powers of 1 over some heavy scale squared. So my heavy scale is lambda, it's arbitrary. So I've got a tower of operators here, which are constructed out of Standard Model particles. So I write down all of the operators I can write down that are SU3 cross SU2 cross U1 invariant and contain only the Standard Model particles. And then they'll have some arbitrary coefficients. So all the BSM effects are contained in this coefficient function here, which multiplies these operators. And the first set of operators here are dimension 6. And then we keep expanding in higher dimensions. So the next set of operators are 1 over lambda the 4th and dimension 8 operators. And you notice I've skipped the odd dimension operators because the odd dimension operators violate lepton numbers. So I've assumed for this example that lepton number is conserved. One can easily relax this assumption if you like. But for the LHC, we'll assume lepton number is conserved. So the first set of operators that are of interest are of order 1 over lambda squared, 1 over big M squared, and they're dimension 6. So they contain things like the 4 fermion operator that I talked about for muon decay. And of course, there are many, many operators. In point of fact, there are 2,499 if you include flavor. But in any given set of experiments, not all operators contribute. And typically when people consider this, they'll consider maybe 20 or 30 operators. So it's a large number, but it's not infinite. And the power of this kind of theory is that it connects top physics, Higgs physics, electroweak physics processes, because this is one Lagrangian that can be applied to Higgs physics. It can be applied to looking for W pairs. It can be applied to vector boson scattering. It can be applied to Drell-Yan. It can be applied to top quark physics. And many of these operators here contribute to multiple processes. So when you're trying to understand what's happening, you can include data from many, many types of experiments. So I'm just going to flash this here because it's not very interesting, except to say that all of the operators are written down in a complete set of operators. So this is the framework for the operators. Many of these operators look like standard model operators where you just add a phi dagger phi to the terms. So for example, if I go up here and I find a nice, let's see, over here in this column. So these are just G mu nu, the kinetic term for the gluon. So just add a phi dagger phi. So these aren't very interesting really because there's no momentum structure. The really interesting operators in this formalism are operators with derivatives. So for example, where's a derivative operator? Over here. So here's a Higgs field, a derivative, a Higgs field, and then two lepton doublets. So when I have the derivatives, I get new kinematic structures. So for example, people are used to using what's called the kappa formalism for looking at Higgs decays, and you cannot get the effects with derivatives in this formalism. So I have new kinematic structures in this kind of framework. Okay, and let me just note that I said jokingly that there are 2,499 operators, but most of those come from flavor permutations of the four fermion operators. So it's a very complicated setup, but the power is, as I said, that operators connect top, Higgs, electroweak precision observables, dibosons. So in a perfect world, you would put all these things together into your sausage maker and see what you could learn. Okay, so the advantage of doing things this way is that this kind of effective field theory is a consistent quantum field theory. What do I mean when I say it's a consistent quantum field theory? I mean that I can do these calculations order by order in inverse powers of this high mass scale, and I can compute these cross sections. I don't need to know the high scale UV physics that generates these coefficients in my Lagrangian, and it's systematically improvable. I can, if I'm strong enough, add the next terms in 1 over lambda. And if I'm even stronger, I can start calculating loop corrections to my predictions. So I can improve it in a consistent way. So at this level, all of these calculations are model independent. I've got my effective Lagrangian. I predict something for, say, z-pole observables, and it doesn't depend on the UV model. So I make the measurement and then I interpret the measurement in terms of the coefficients of this effective Lagrangian. Then I compare very different classes of measurements. Well, it sounds like magic, right? Too good to be true. So the devil is always in the details. So how does this actually work in practice and how model independent is this? That's what I want to get into in the next part of the talk. So how am I going to learn from the SMEF? So it requires a number of ingredients. So I match my experiment. So I need very, very precise experimental measurements. I'm going to perturb around the standard model theory. So I need very precise standard model calculations. And then I'm going to try to extract precise SMEF bits. So the SMEF contributions to an observable will just be given in terms of these coefficient functions that multiply these operators. So what I want is this top plot, and I stole this from Julia Zandarigi because it's a beautiful graphics. So I want my data to have very small error bars. I want my theory predictions to have very small error bars, and I want my SMEF predictions to be here in a way that I can believe them, so that if my data goes like this, I can say, aha, I'm on this blue line and not this green line. But what I don't want is this kind of thing at the bottom where my uncertainties on my theory are too big to extract anything from the LHC data. So understanding these uncertainties in the SMEF is a work in progress. There's a lot of theory work on it, and I think it's fair to say that there's no theoretical consensus as to how to get this green line on the SMEF predictions. So once I get these SMEF coefficients, then I'm hoping that what I'm going to learn is that there will be a pattern in the non-zero coefficients. So I'm going to measure my data, and I'm going to interpret in terms of this theory, and hopefully I will measure some coefficients that are not zero. And this is an unambiguous signal for new physics because, like I said, I'm perturbing around the standard model. So if I measure any of these coefficients here non-zero, it's got to be new physics. And then I can try to interpret these in terms of the ultraviolet model. So that's really the goal of doing this. So let me start by what you all know and love, testing Higgs couplings with what's called the kappa framework. And the kappa framework is really, really simple. So you assume no new resonance, zero width, and no tensor structures. So I calculate sigma times branching ratio for some Higgs process just in terms of fudge factors. So the Higgs coupling to, say, B's is just a fudge factor kappa, and the Higgs coupling to W's is another fudge factor kappa, and then I extract limits on these kappas. Okay, but this is a no good, terrible way to do things. It's theoretically inconsistent. In the standard model, the coupling of the Higgs to fermions and to gauge bosons is absolutely predicted, and it's got to be 1. Gauge invariance requires that kappa is 1. So this isn't a consistent field theory, and I cannot take the kappa framework and systematically improve it. Whereas if I have an effective field theory, I can improve it. So let me just give you an example of a Higgs decay. Okay, and I know I'm not supposed to put equations in colloquiums, but I have a few because that's the way I think. So suppose I have the decay of the Higgs to B's, and I'm looking for how it deviates from the standard model. So in the kappa framework, it's just 1 plus, say, delta kappa B. So I can translate this into an effective field theory formalism where this delta kappa B is given just by a combination of these coefficient functions in this effective field theory. So there are a bunch of coefficient functions, and they come from different places. The interesting coefficient function is this coefficient function CDH, which modifies the fermion-Yukawa couplings. But all in all, you look at this and you say, isn't this just a fancy way of writing the kappas? You've got all this formalism, but when all is said and done, all you've done is redefine this kappa in terms of other stuff. And yes, for the B decays, it's exactly the same because there is no momentum dependence in any of these operators. So they're just there. They don't do much. But suppose now I start thinking about Higgs decaying to 2 Z's. So in this example, Higgs decays to a virtual Z, which then goes to 2 fermions. So I'll do the same thing. I'll look at the Higgs decay to a Z plus 2 fermions normalized to the standard model. So there'll be 1 plus this overall factor, and then 2 combinations of coefficient functions in my effective field theory. But now it's different because this first combination, little c sub k, is just these coefficient functions that I had in the previous slide, coefficients that depend on operators with no kinematic structure. So it's boring. So yes, this is just an overall rescaling. But this second term comes from operators which have a momentum dependence. And this 0.97 here, this comes from kinematic factors in the decay. So if I look at this decay and I look at, say, the Q squared of this FF bar pair, and then I put some cuts on it, this will change depending on the kinematics. So this is not just a constant rescaling of the standard model. It really has momentum dependence in it. So when I'm looking at the Higgs couplings to Z's, I get these effects that depend on kinematics and will not be captured within this kappa framework. So I'm learning something new in this effective field theory. Okay, so let me just recap. The momentum-dependent operators change the shape of the distributions. I gave you the simple example of Higgs going to Z and 2 fermions, but of course it's all over the place. Here's a recent plot from Heinrich and her collaborators of Higgs plus jet production, looking at the PT of the Higgs. So here's the PT of the Higgs, and you note here again, many orders of magnitude here. So down here is the ratio to the standard model. And so the blue crosses here are in an effective field theory where these coefficient functions of the dimension 6 operators are not zero. So you can see in this example, at high PT, you're seeing effects which grow with PT squared over this lambda squared. So in this example, there are about 40% effects, and they're chosen, the values that are chosen is this example are chosen such that the Higgs total cross-section comes out to be the measured value. So this is 100% allowed by experimental data, and it shows you how you can get effects from these momentum-dependent operators at high PT. Okay, so then we can ask this question, well, when does this whole thing make sense? And let me go slowly here because this is the subject of a lot of theoretical angst. So I'm taking my standard model Lagrangian, as I've said, and I'm expanding in terms of powers of dimension 6 operators, dimension 8 operators. My Lagrangian goes 1 over lambda squared, 1 over lambda to the 4th. So I want to calculate some cross-section. So I'm going to calculate my cross-section here. There's some piece that comes from the standard model. Then there's some piece which comes from these dimension 6 operators, which goes like 1 over lambda squared. And typically the calculations that we have these days just include this 1 over lambda squared contribution. So I'll square this and I'll expand it. So then I've got the standard model piece. I will have the interference of the standard model with this dimension 6 operator, 1 over lambda squared. And then I'll have a piece that just comes from squaring this piece. So it's the dimension 6 piece squared over lambda to the 4th. Okay, so the problem here is that these terms, which come from squaring the dimension 6 piece, are exactly the same counting in 1 over lambda as the dimension 8 pieces, which I've neglected. Well, okay, you say, let's just drop these 1 over lambda to the 4th pieces. And then I've got a nice expansion to order 1 over lambda squared. But if you remember quantum field theory, if I don't calculate the absolute value squared, this interference piece here isn't guaranteed to be positive because I haven't calculated an absolute value squared. And so it's super easy to get predictions where the cross-section goes negative. And of course, you all know that cross-sections can't be negative. So what that tells you is that you've done an expansion that's no longer valid. So you have to keep these terms such that the 1 over lambda squared piece is much, much smaller than the pieces you've dropped. So this is where you get into problems with the effective field theory, which terms to include. Because I can't include all the dimension 8 pieces. There's simply too many of them to include. But if I just randomly start dropping these pieces, well, then I get into trouble with my expansion here. So there's a certain counting law that you can use with the effective field theory, which says that, well, really the standard model has some standard model coupling. Think about the weak coupling in the standard model. And my BSM theory, which generates my effective field theory, has some BSM coupling here, whatever it is. So then when I start squaring my cross section, so I've got my pieces, which I had before, which I was going to drop the 1 over lambda to the 4th, which come from squaring my dimension 6 contributions. And then I've got my pieces from my dimension 8 contributions, which I'm dropping. And they're sort of the same order of magnitude, as I said before, leaving you to be a little bit queasy about this. But then I can say, well, maybe the dimension 6 squared dominates if the BSM coupling is very, very big. So the state of the art typically uses just the dimension 6 operators, and then it will compare the pieces where I just include this piece and where I include this piece and see how they're different. So the implicit assumption is that the BSM might be a little bit bigger or is bigger than the standard model piece. But you can see as you start dropping terms in your effective field theory expansion, the assumptions are creeping in a little bit. It's no longer as model independent as you thought it would be. And that really comes from the fact that I'm trying to do an expansion in order 1 over lambda squared, but I'm actually calculating a cross section, which requires an absolute value squared. So these assumptions kind of creep in here, and it's inevitable. So the experiments have started to do limits on these kinds of effective field theory operators, and they come from various sources. And this is a plot from Atlas from about a year ago, and it's a beautiful plot because what they said was, let's look at the limits that come from the fits to the Higgs, the fixed to gauge boson pair production, say W plus W minus, and electroweak precision observables, which I've listed here. So they put together data from different sources. This particular plot does not have data from top quark physics, but it has data from the different sources. And what they show is limits on various coefficients, and it doesn't matter what these are here, that come from the different sources. And so some of the limits, the red is Higgs, come almost entirely from Higgs physics. Some of the limits come almost entirely from electroweak precision observables. And some of the limits you can see here have contributions from different sources. And again, the fact that some things are limited by different pieces of data is the real power of this approach. And you can see that everything kind of lines up. This line 1 here is the standard model. So everything kind of lines up. And so somebody is going to ask me about this outlier over here, this blue piece. And this, you see, comes almost entirely from the electroweak precision observables. And it's a puzzle that's been hanging around since SLD and the precision data from LEP, because it's the right-handed coupling of the B to the Z's. It has been off since forever. So everything else lines up with the standard model. So then you can do global fits to different pieces of data. So here's a global fit to Higgs data, which again, I apologize to CMS. I'm at an Atlas institution, so I'm more familiar with the Atlas data. So this is an Atlas fit to just Higgs data. But what they do that's really interesting and that teaches you about the effective field theory is that they did a fit first, including only the 1 over lambda squared pieces, which we call linear pieces, and then including the 1 over lambda to the 4th pieces from the square of the amplitude, which we call the quadratic pieces. And you can see that there's not a huge difference between the fits. And in fact, you can see that the stuff that has good limits, the two fits are very close, telling you that the expansion is really good. And the stuff where the limits aren't so good, up here, you can see that there's a bigger difference between the linear and the quadratic fit. And you can also see that typically the experiments probe on the order of the 1 to 10 TeV scale, if you assume the coupling is 1. So we're probing 1 to 10 TeV with this big assumption that the coupling is 1. Okay, so there are a lot of global fits in the world by various consortiums of theorists. This is one of them here. And the reason I put this plot here is because this plot includes not only Higgs data and not only W pair data, but it also includes top physics. And so the top is a new player that people have started to put top data into the fits. So the blue are fits which include only the Higgs data, and the orange include the top plus the Higgs plus W pairs. And that you can see that for some interactions, they're not so different. And for some interactions, they're radically different. So what this says is that when we go to look to see how we can learn new physics by looking at these effective field theory approaches, you really need to include top quark, Higgs, WW production. This particular plot does not have electroweak precision observables, but you can see that for a lot of things, you get the same answer with and without the top. But again, you learn new physics when you include the top. Okay, so let me just talk a little bit about the power of loops, because one of the powers of this kind of theory is that it's a consistent field theory, so you can start calculating loops. You can calculate loops all over the place. So you can use standard techniques. There's nothing particularly new in the way these loops are calculated. The QCD loops have been automated, so you can run and get the QCD corrections by running automated tools, which I'm not going to talk about. But the electroweak effects you have to do on a case-by-case basis. But you can really learn some new things. So for example, from the Z-pole observables, they're very, very precise measurements of Z goes to E plus E minus, but they don't constrain this TT bar interaction very precisely. And for example, you can also learn from, say, Drell-Yan about the Z W plus W minus interactions. We learn about the Z W plus W minus interactions from W pair production, but you can actually learn more from looking at Drell-Yan production because it's incredibly precisely measured. So when you start calculating loops in this effective field theory framework, what's going to happen is you're going to gain sensitivity to interactions that you're not sensitive to at tree level. So here's just a simple example about the future. So we think we might want to build an E plus E minus machine, FCCE, to look for Higgs couplings. So you would look for E plus E minus to Z Higgs, where the cross section is maximized at the lowest energy, 240 GeV. And then you can look at it in this SMEF framework. So you can look for E plus E minus goes to Higgs plus Z. And then once you start calculating loops, you can be sensitive to the TT bar interaction with the electrons. You could be sensitive here to the Higgs trilinear interaction. So you can look at fits to these and projections for the future. So here's an example of how you might be sensitive to the Higgs self interactions, this HHH vertex, and to the electron-positron TT bar interaction with a correlated fit. So here is the, let's see, the orange here is at 240 GeV. So the interactions and the sensitivity is correlated. And then if you measure at another energy, say 365, the correlations are different. And so you can really pin down this Higgs trilinear coupling and this TT bar E plus E minus coupling by doing precision measurement at E plus E minus goes to ZH at future machines. And just to point out, the yellow here is what we know from Z-pole. So you're going to learn new things by measuring Higgs drilling at these future colliders. Okay, you can look at the future colliders and look for CP violation within this framework of an effective field theory once you calculate these loops. So you can get limits on operators that violate CP, and they're just listed here, two of them. They involve W, Z bosons, and CP violating asymmetries. And of course, you think that CP is mostly limited by electric dipole moments, but electric dipole moments span a line in this plane, and the E plus E minus machines span a line which is different. So by putting electric dipole limits with E plus E minus to ZH, this line here, and combining them perhaps with the current atlas limits, which is the yellow blob, you can really pin down these CP violating operators at the future colliders. So this provides a very powerful theoretical framework for looking for new physics. And as I've said before, the power is that you can put together these pieces of information from different experimental sources. Okay, so I misspelled colliders. Okay, I'll fix that. Sorry about that. So the future colliders, they need this NLO SMEF, because if I look at projections for how well I'm going to limit various coefficient functions at different colliders, the projections depend very sensitively on these higher order corrections. So we need to include these. And this was part of what I started talking about at the beginning. You need the really precise experiment, but you need the really precise theory to match up to this. Okay. So these loop corrections generate logarithms and they generate constant pieces. And so these plots that I've showed you, let me go back. These plots are full calculations. They're not just the renormalization group running these logarithms, which you can get for free. They're all known, but includes these dots here, all the constant pieces, and they actually make a difference here. So from a theory point of view, the QCD corrections are known, they're automated, we've got them. But these electroweak pieces, which are going to let you combine things like EDMs with these fits to coefficients, they're not automated. So this is a growth area of theory, looking at these on a case-by-case basis. So these NLO corrections open this window to these new interactions, for example, the Higgs trilinear coupling, but you need the full calculation to get the story. So let me just end my colloquium by asking a question. Who cares? I don't really give a hoot about the value of CXY is 0.007. These coefficients in and of themselves don't tell you anything, but they tell you that there could be new physics. If you actually did this approach, you don't find any new resonances, but you do a careful SMEF fit to all your data, and you unambiguously measure some non-zero value for one of these coefficients. It's new physics because I'm perturbing around the standard model. So the search for new physics is really the search for these non-zero coefficient functions. And the power of this is that if I measured a non-zero coefficient function, then I can match it to some high-scale model of underlying physics, and I can gain some new information about what the high-scale physics is. So different models are going to have different patterns of coefficient functions. So what I've done here is just generically pick some of my favorite coefficient functions. It doesn't matter what they are here, but what does matter is that if I have different types of models, for example, these are scalars which are singlets under SU3, SU2 cross U1. So here we go. Here's a 2 Higgs doublet model. Here's a model with a top vector-like quark. Here's a model with a colored scalar. And you can see that you get different coefficient functions. So if I measured, say, this guy over here was non-zero, that would tell me something. And it would tell me something about the type of model that I could have. So this would let me see that there was high-scale physics, even though I couldn't measure the physical particle. Okay, so I want to address the inverse problem, the who cares problem. So if I measure these non-zero coefficients, can I really determine the underlying high-scale model? And the answer is, well, sort of. In a simple model, so suppose I have a model which only has one new massive particle, and the interaction is described in terms of a single parameter. Then the types of coefficients that I can get, it's been categorized years ago, and we can look for limits on the kinds of masses we might get in these particles. And let me remind you that the coefficients we're looking for are c over lambda squared. So any prediction I make, including just these dimension 6 operators, only depends on the coefficient divided by lambda squared. So when somebody tells you that, oh, I've ruled out particles of mass, what is it, 6 TeV for this case. Well, that assumes that the interaction strength is 1. So they rescale in an obvious way of coefficient over scale squared. So what we have today is that there are limits on things like triplet gauge bosons, scalars, neutral gauge bosons that are typically, here's 3 TeV, 4, 5. So the kinds of mass limits we're getting from this type of fit suggests that in simple models like this, the scales are already up above maybe 3 or 4 TeV. So you can actually also do this at loop order, and the loop corrections to the matching have been done now. So this plot shows NLO means that instead of just matching to some high scale theory at tree level, I've matched to loops. So the loop matching is automated in this code and probably in other places. And for most models, the loop matching effects are small. So these coefficients, as I mentioned, they all have a scale. And the scale dependence of these coefficients is well known. But what happens is if I have a model where there's some new physics at a very high scale, which I always call lambda, my measurements are at the weak scale. So I have to take my predictions from the high scale to the weak scale. So although my model might not have these coefficients down here, when I start scaling from the weak scale to the high scale or vice versa, I generate new coefficients. So coefficients are generated through this running from the very high scale where I have my model, which explains everything, to the W mass, say, where I make my measurements. So I can actually have renormalization group generated effects. So there's a lot of people studying this, and it's actually super interesting because I can generate effects which might have very strong limits. So let me just show you a plot here, which is a plot of how all these studies go. So suppose I do some global fit where I match to this effective field theory at a high scale, and then I run all these coefficients down to the W mass or the Z mass, and then I extract my limits on the model. So what's going to happen is I'm going to extract limits in some correlated plane. So this particular interaction here is a Higgs trilinear coupling, which we know and love. And then limits are extracted by looking at electroweak precision observables, Higgs physics, putting them all together. And if I have my model, it's going to be a point on this plane. So the experiments will extract correlated limits on any two parameters. And then my model is going to tell me, aha, if it's a model with a scalar singlet at the high scale, it's got to sit right here on one of those circles. So by measuring these coefficients, I'm going to learn something about this high scale. Okay, so I can play the, I'm sorry, I apologize, this plot came out poorly. I can look for many types of new physics. So this is an example where I look for heavy Z primes. So it looks for many different types of models of Z primes and says, well, what does the data tell me about these Z primes? So the data basically tells me that most of these Z primes are above 4 TeV by looking at this effective field theory approach. And the reason I included this plot was because most of the things I've been talking about included the first terms in the series, the dimension 6 1 over lambda squared pieces. This particular study included the next terms in the expansion, the so-called dimension 8 pieces, the 1 over lambda to the 4th pieces. So it was matched to dimension 8. And in this example, these higher order terms gave a very, very small contribution. So again, looking for heavy Z primes by looking for their effects on coefficient functions, there's information from many places. And so this shows information from electroweak precision observables and from Drell-Yan. Oops, sorry, and from Drell-Yan. So in any given scenario, you're going to get information on coefficients, and you're going to put it together to try to understand what the underlying model is. And you need all these different sources to get the information. So let me just close with the 2 Higgs doublet model, because I think it's something that's familiar to many of you. And the 2 Higgs doublet model is actually an interesting test case for learning new physics by looking at effective field theories, because the 2 Higgs doublet model is more complicated than these scenarios which just have one new particle. So it's got the 2 Higgs doublets, so it's got 5 physical Higgs bosons, and it's got essentially 2 parameters that we can play with. It's got a mixing angle alpha from diagonalizing the neutral Higgs mass matrix, and it's got the ratio of vacuum expectation values, tan beta. So if I look at the scenario where an effective field theory approach is appropriate by taking all of the masses to infinity, what happens in that limit is I'm also taking this parameter, which is a central parameter of the model, cos alpha minus beta, to be suppressed by order 1 over m squared. So all the dimension 6 coefficients are proportional to this cosine alpha minus beta here. But the gauge couplings are proportional to the sign of this parameter, and that they come from dimension 8 operators. So this is an example of a model where you can't capture the physics by including only the dimension 6. So this is a 2 Higgs doublet plot looking at limits on this mixing parameter, cos beta minus alpha, and the tan beta, which is the ratio of Vebs. And the experiments have done a global fit to the Higgs data, but this is a theory plot. And what this shows is that if you have the exact theory curve, which is this red, which is this red curve here, you don't reproduce it by only including the dimension 6 terms, but you really need to go to the next order in your effective field theory expansion. And in this case, we understand why we need to go to higher order. It's because there's new physics coming in, the coupling of the Higgs to gauge bosons in this scenario. Okay, let's see here. So let me just end this by saying, well, if you think back to my very beginning slides, I made a big assumption. I said the Higgs is part of an SU2 doublet. But of course, it doesn't have to be part of an SU2 doublet. Perhaps it's just a singlet under our standard model gauge interactions. And this is what's called the HEF, the Higgs effective field theory. And the expansion is different from the one I've been talking about. And in particular, if you look at the Higgs self-interactions, they're just essentially free parameters. So there's a Higgs cubic interaction, and there's a Higgs quartic interaction, and these are free parameters. In the standard model, they're one, but in this effective field theory, they can be different. And in particular, if I don't assume that the Higgs is in an SU2 doublet, then the new physics will come into the Higgs self-interactions and WW going to Higgs-Higgs, which is the vector boson production of the two Higgses. So if I could measure things like WW goes to two Higgses, it could potentially distinguish between these two types of effective field theories, which would be an interesting thing. So the SMEF can always be written as a Higgs effective field theory, but not the other way around. And in particular, people have looked for signals. How could you tell if you have a Higgs in a doublet or a Higgs which is not in a doublet in these two effective field theory? And this is a plot, which is actually, this is a CMS plot. Good. So these two things on the axes, which are labeled kappa, are HEF parameters. So they're parameters in this effective field theory where the Higgs is not a doublet. And the limits are these yellow curves here. So if I had a standard model effective field theory where the Higgs was in a doublet, it would have to lie on this red line. So if I measured something down here, it would tell me that the Higgs was not in a doublet. So that would be an interesting result. So in the future, these measurements of Higgs pair production from vector boson fusion have the potential to tell me if the Higgs is in a doublet or not. So, okay, let me stop here and say that this approach is an approach that may be able to extract insights about new physics, even if there's no new physics that we can directly measure new particle production. And it could be the only tool we have. If we don't see these particles in an energy range that we're sensitive to, we can still do these very precise measurements, extract these coefficients, interpret these coefficients in terms of new physics. And the experiments have begun to produce these results by combining input from different types of physics. We really, really want these studies to be done by the experimentalists and not by the theorists, so that all the correlations and things are in there correctly. And let me just say that, in my view, the most pressing theoretical need is for the theorists to come up with a consistent way to understand the uncertainties of these measurements. Thank you.